Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Well, very good. I think we are just about ready to roll. It's a great pleasure to have in the lab again Bernhard Schulkopf. I say again because when I first came to the lab, which is nearly 16 years ago or something, Bernhard was here already as a scientist. But he's been on a long journey since then, involving going via New York to become director of the Max Planck Institute, where he is now, except it's a slightly different Max Planck Institute when he started. And in the meantime, he has, I would say, transformed our understanding of kernel learning, and everybody, even close to that field, now uses his ideas. And he has been a remarkably innovative scientist, and more recently has got into the issue of causality in machine learning, which is a fascinating issue. And Bernhard, we're very much looking forward to hearing what you have to tell us about it.
Thank you very much for the introduction, for the invitation. It's a great honor to be here. It's also a great pleasure to be back here. I have very fond memories of my time in Cambridge. These were some of the best years of my life. And I also learned a lot. In particular, I learned that the world is not just kernels in VC dimension. But there's also Bayesian methods and things like that. And maybe you will see some influence of this in today's presentation, which is partly about kernels, but not only about kernels. So let me start with an application. So I work in machine learning and machine inference, and of course this has many applications in science and industry. And for instance, if you're looking on a shopping website for this item called a glass circular cutter, then from past purchases of other customers, Amazon can recommend what else you might be wanting to buy, and give you some suggestions, such as this item here, a balaclava, this baseball bat down here, or maybe a little bit surprising, this rucksack with bat wings. So there are various things that you might want to buy. And let's be a little bit more abstract now and think about machine learning more abstractly and about inference. So let's assume we have measured two observables, x and y, and we found them to lie approximately on a straight line. So we might be willing to infer a corresponding law of nature. Now, already Leibniz thought about this kind of problems, and he pointed out that even if we scatter spots of inks randomly, for instance, by taking a quill pen and shaking it over a piece of paper, we would still find a mathematical equation that is satisfied by these points. And Leibniz argued that we wouldn't call this a law of nature, because no matter how the points are distributed, we can always find such an explanation. So according to Leibniz, the explanation should be simple in some sense. And of course, this begs the question of what makes the equation simple. And a lot of people have thought about this from the mathematical point of view, such as Leibniz, Weil, Chaitin, Vapnik, Chervonenkis. Now, if you're a physicist, you could have a more pragmatic view. And this physicist here, Rutherford, he said, if your experiment needs statistics, you ought to have done a better experiment. So I'll try to convince you that there are interesting inference problems where better experiments are not enough. So inference problems that are non-trivial in some sense. And I think we're currently experiencing a revolution in the natural sciences, and maybe not only there, where people try to solve exactly those problems. And it turns out that learning and inference plays a central role in this. So here's an example. So in this example, it's from bioinformatics. We train a support vector machine to solve a certain classification problem based on human DNA sequence information. It's reasonably high dimensional. The training set consists of 15 million sequence snippets. And it doesn't matter what exactly this curve shows. The main message is down here, if we only have 1,000 training examples, the performance is essentially chance level. But as we move up here to 10 million or more training examples, performance gets very good. So it's it's a regularity in the world, it's not chance. But probably as humans we wouldn't see it because we wouldn't be able to look at 10,000 of these examples. We wouldn't be able to make any sense out of such a data set. So it's a structure that we wouldn't see, and I think that's really quite interesting, and it's highly non-trivial to find it. And some characteristics of these kinds of problems are that they are high dimensional. They are complex, for instance, nonlinear or non-stationary. We typically have little prior knowledge, so we don't have a mechanistic model of what exactly is going on. And therefore, as a consequence of all these issues, we need big data sets. And of course, to process them, we need computers, and we need automatic inference methods and machine learning methods. So the core problem of machine learning is called generalization. And I'll try to illustrate it with a little toy example. So suppose we've seen these 4 digits and ask what's the next digit. I think any computer scientist can answer this question. Any guesses? 11. That's a very good answer. This is called the lazy caterers sequence, because it's the number of pieces into which you can divide up a cake with n cuts. You just make sure that every cut intersects all previous cuts. But 12 is also a good answer. 13 is a very nice answer. It even has a name. 14 is a nice answer. In this case, I would predict that the sequence ends. This is also a nice answer, which was proposed by a former postdoc of mine, which combines the decimal expansions of pi and e. In fact, you don't even need e. You can go to this nice website, which lets you search for digit sequences in pi, and then you find out that it occurs at position 16,992. And here's how it continues. So that's a very compact description of this sequence. And there's this website, online encyclopedia of integer sequences. You get 600 hits for these digits. So obviously that can't be the answer. And if we ask which continuation is correct, then there's really no way to tell. And this is called the induction problem in philosophy. Now, in statistical learning theory, we're trying to answer or to ask a slightly easier question, maybe. We're asking, how can we use observed data to come up with a law that's correct, or that's typically correct, or that's with high probability more or less correct? And this is close to what Karl Popper called Kant's demarcation problem. So it's also a classical problem of philosophy. It's a problem what separates physics from metaphysics. So what kind of methods should you be using to call yourself a physicist as opposed to a metaphysicist? And Vapnik Chermenkis tried to answer this kind of question starting in the 60s in the Russian Institute for Controlled Science at the Russian Academy of Science as PhD students. And they studied this simplest scenario of machine learning, which is called two-class classification or pattern recognition. And in this problem, we're given observations consisting of inputs x and labels plus minus 1. So for instance, these could describe the class of a handwritten character. Is it class 0 or 1? We assume there's an unknown regularity modeled as a probability distribution. And this is a regularity we think has generated these observations. And now our goal is to minimize what's called the risk or the expected error for future data drawn from the same distribution based on these training observations. Now we can write down the expected error in the future. We can't compute it because we don't have access to this distribution. We only have data from the distribution. We can approximate this quantity in terms of an empirical quantity. This would be called the training error. And then we can ask ourselves what happens if we minimize the training error. Will we get a solution which is close to minimizing the future error? And the answer is, in general, that this doesn't work. We need additional conditions or assumptions. We need conditions on the class of functions over which we minimize. Essentially, the class of functions shouldn't be too complex. If it's arbitrarily complex, then we can explain the data no matter how we're shaking the quill pen. And one way to capture the complexity of such a class of functions is now referred to as the VC dimension. So this is a notion that they came up with as PhD students, which is now the basis of whole branches of mathematics and empirical process theory. And the main statement is this process of minimizing the training error, it's called empirical risk minimization, is consistent. So in the limit, it leads to the right answer, independent of what regularity has generated the data, provided that the VC dimension of the function class is finite. Now, maybe I don't need to define the VC dimension. Message is it's a measure of complexity for function classes. It's a combinatorial measure. It's difficult to evaluate for complicated function classes, but we know how to do it for linear function classes. That's nice because afterwards we will reduce something else to the linear case. So we can do it for linear function classes. What if the problem is not linear? So here we have a typical nonlinear decision problem. We want to separate these blue crosses from the red circles. The true decision boundary is this ellipse. It turns out, if you think about this for a second, if we first transformed all training points using this nonlinear mapping, map them into a higher dimensional space, to this three-dimensional space spanned by these three coordinates, then we could suddenly solve this classification problem using a linear equation, so using what's called a hyperplane. And what's nice about this trick is that actually if we wanted to compute dot products in this three-dimensional space, it turns out the dot products reduce to a simple function of the two-dimensional inputs. And this is called the kernel trick, and this is an example of a degree 2 polynomial kernel. And the same thing also works for higher degree kernels, so not just degree 2. And it also works for n-dimensional or d-dimensional inputs. So we can use this kind of trick to implicitly compute dot products in higher dimensional spaces of points that we have non-linearly mapped into these spaces. Same thing even more generally works for everything that satisfies a condition of positive definiteness. So whenever we have a so-called positive definite kernel, or a covariance function, as some people prefer to call it, we know there is such a representation in a higher dimensional space that we call the feature space. And in this space, we can do all sorts of things. We can, for instance, kernelize, as people call it, a linear algorithm, such as a principal component analysis, which then leads to something nonlinear. In this case, it leads to a different and interesting data feature extraction method. The first two nonlinear principal components would separate this simple data set into the three clusters, and then the higher order components would start looking for structure within the clusters in an interesting way. So for instance, this component is orthogonal to this one, this is roughly orthogonal to this one, etc. And this contains various other approaches as special cases. Now, a support vector machine, I think a lot of people know about this. So very briefly, uses the same idea. It maps data, or it actually has used this idea already before. It maps data that may not be linearly separable or modelable into a high dimensional space. Then it computes a linear solution. In this case, it's a separating hyperplane with a large margin of separation. The reason being that for this we can control the VC dimension, so we can make sure that our method generalizes well, and then this linear separation, the high dimensional space, will correspond to a nonlinear separation in the input domain. So I have a little video here. We start with a mapping into the feature space that's almost linear by taking a Gaussian kernel that's very wide. And then I gradually turn up the nonlinearity by making the kernel more narrow. And you can see that this decision boundary becomes more and more nonlinear in this case. And there's various nice properties of these approaches. One of them being that we can prove that the solution is always an expansion in terms of kernel functions, and that it can be computed by solving a convex QP and various other aspects. So in all cases, we generate nonlinear surfaces in these high-dimensional feature spaces, and those we generate linear surfaces in the high-dimensional space corresponding to nonlinear surfaces in the input domain. And these nonlinear surfaces could look rather complicated. So this is an example of an application in computer graphics or computational geometry, where we approximate point clouds and then actually developed a method to morph between different sets of point clouds, which led to this automatic method for morphing shapes. So in all machine learning methods, certain issues have to be addressed one way or another, and I think it's nice that kernels provide a unified framework to do so. So the three issues are: we need a notion of similarity that we use to compare data points. It's especially important if the data points are not vectorial to begin with, if they are, for instance, strings or graphs or something like that. The kernel induces a linear representation of the data, so it implicitly tells us how we represent the data when we process them. And finally, it encodes the function class because, as I mentioned before, one can prove that the solutions to kernel algorithms are expanded in terms of kernels. There's much more to kernels, though, and in recent years there have been some interesting developments where they were used in a slightly more general sense. And for me, the starting point of this was a tutorial example, which we came up with when we were working on this book that I had on the last slide. And a lot of this work was actually done while I was at Microsoft. So this is a trivial algorithm where what we try to do is build a classifier as simple as possible. In this case, we have 2 point clouds. We map them into the feature space. Then we classify a new point based on whether it's closer to the mean of the one cloud or to the mean of the other cloud. Now, obviously, this induces a hyperplane decision boundary in this high-dimensional space, and you can ask yourself, what does this hyperplane correspond to or what does the decision function correspond to in the input domain? And it turns out it's a so-called plug-in classifier based on Parsons Windows estimate, but it's actually a little bit more general because these kernels don't need to be valid density models. Now that's interesting. So here we have a point set that corresponds to a density in some other space. And actually we can think of this more generally. We can think of the feature map, this mapping that takes points and maps them into the higher dimensional space where we apply our linear methods. We can think of this as a mapping not just for points, but actually also for sets of points and even for continuous probability distributions. So if we take a set of points, we define the mapping just to be the average over the mappings of the individual points. In the case of distributions, we define it to be the expectation over this distribution. And then by the choice of a kernel, we determine how much information we retain as we map this object into the higher dimensional space. So if we choose a linear kernel, we just retain the first moment, so the mean or the expectation. If we choose a polynomial kernel, we retain the moments up to order n, so either the empirical moments or the analytical moments of a distribution. And if we use a slightly more restricted class of kernels, which is called either strictly positive definite or characteristic, then it turns out we retain all the information. So we don't lose anything. So all the information about a data set or about a distribution is stored in this one element in the feature space. And then we can ask ourselves, what can we do with these kinds of elements? What kind of linear methods can we apply to such elements to perform inference on distributions? And there are various applications or special cases. One is something well known from statistics. It's called the moment generating function. This is a special case for one particular kernel. We can also do independence testing. If we map the product of 2 marginal distributions and also the joint distribution of 2 random variables and compare how they lie to each other, what's the distance in the feature space, we can construct independence tests. We can construct homogeneity tests, which means testing for whether some data has been generated by the same distribution as some other data set. And one can do things like base updates. One can give nice physical interpretations connecting this to wave optics. And finally, a problem that I've been working on more recently, but I think I won't go into detail today, is related to probabilistic programming. So if you think about programming or what probabilistic programming might mean, so from my point of view, it could mean that we lift all operations that we can define on standard data types to distributions over these data types. So I'm not thinking of something specific to perform a certain type of inference. I'm just thinking of operations on distributions over data types. And it turns out that if we have some distributions and embed them into such a feature space with this kernel mean mapping, then we can give an elegant way of performing general arithmetic operations on such embedded distributions, which is a non-trivial problem, because if you think about it for a second, suppose you had 2 distributions, let's say very simple, if they're both Gaussian and you want to compute the distribution of the sum. So I should say it more precisely, you have 2 random variables that both have a Gaussian distribution. Now you want to know the distribution of the sum of these random variables. In this case, it's doable. It's a convolution of the 2 densities, assuming we have densities. If you have a more general function, if you have a product, you can still do something. If it's something more general, it's very complicated, and people essentially resort to sampling. So this gives us a nice approach that in some sense generalizes the sampling or provides some kind of smooth sampling for this kind of problem. But I think I'm going to skip over this one and instead get to the main part of the talk, where I want to talk about causality and about what motivated me to sort of leave the standard machine learning field, at least part of my time. So these methods, I didn't talk about applications, just about methods so far, but there are lots of applications, and these are used everywhere. Your cell phone uses them, your camera uses them, and I think you have lots of applications that were developed in this lab here, of course. And also we have a relatively good understanding of how and why they work, as long as nobody intervenes in the underlying system that generates the data. Unfortunately, this assumption is often unrealistic, and then things can break, sometimes in embarrassing ways. And I want to illustrate this with another shopping example. In this shopping example here, we have a person who is shopping for a laptop rucksack, and then the website recommends that along with the rucksack, the person should buy a laptop. Now this sounds funny. It feels somehow wrong. If we think about it, why it feels wrong, then we would probably say intuitively, we would think that buying the laptop can be a cause for also wishing to buy a rucksack. And so buying the rucksack is not a cause, but buying the rucksack is an effect of already having the laptop or having decided to buy a laptop at the same time. So both the cause and the effect contain information about each other, of course, but in some sense for different reasons. So the cause contains information about the effect because it controls the effect. The effect contains information about the cause because it carries some kind of footprint of the cause. If you measure this in terms of information theory, using mutual information, then mutual information is a symmetric concept. So you wouldn't be able to distinguish between these two dependencies one way or another. So if we only look at that, which in some sense is what machine learning is doing, then this directionality is lost. So it seems there's some kind of causal process going on in the real world, which has generated statistical dependence that we observe. But as soon as we only look at this statistical dependence, using machine learning, for instance, we have lost this underlying reason for the dependence, which is, in other words, we could say what we have done is we have imitated the exterior of a process. This is a quotation taken out of context. I'll tell you where it's from later on. So what we've done, we've imitated the superficial exterior of a process without having any understanding of the underlying substance. So that's what we do if we do standard machine learning. So let's look at another example that also tries to illustrate this difference between statistical dependence and causality. And that's a well-known example about storks and babies. So if you look at the frequency of storks in European countries and the human birth rate, you find a strong correlation between the two. Of course, everybody knows that storks don't bring the babies, so we wouldn't infer causality from this. But there are much more subtle examples where it's essentially the same, and we do think we infer causality. So this is quite a tricky point. But the main point is that we would not try to increase the birth rate by increasing the number of storks. Nobody would believe that this kind of intervention would lead to the desired outcome. So the statistical model doesn't make predictions for this kind of intervention, and in fact the intervention in some sense also violates the typical what we call the IID setting, independent identically distributed data. So it's tricky, and in summary so far we could summarize saying that causal links seem to generate statistical dependence, but vice versa it's a bit more complicated. So they are related, but they're not the same. And Hans Reichenbach, this very interesting physicist and philosopher, had a profound insight into the link between causality and statistics. And I think even today, many methods are still based on this essentially. And what he was postulating was that if we have two observables that are statistically dependent, so think of them as the storks and the babies, then there must be a third observable that causally influences both of them. This third observable, I should say, could coincide with one of the two, so there could be a direct causal link, but the generic case would be that the third quantity has a causal effect on both of them. So for instance, there could be storks, babies are related, and maybe there's a confounder that says the development of the country or something like that, or the space that you have, or I don't know, various economic issues. So this confounder has a causal effect on both of them, generates a dependence between the observed quantities. And moreover, Reichenbach was postulating that this third observable screens X and Y from each other, in the sense that if we condition on the third one, then X and Y become independent. So that's nice, and it leads to, or here is a model of causality which can be shown to satisfy the Reichenbach principle. It's almost equivalent, but there's some details that I won't go into. And in this model, we assume we have a set of observables that are connected by arrows. These arrows represent direct causal links. So that's where the causal semantics comes in. Each observable, so let's think of this green one, is determined by its parents in the graph and by a variable u. U stands for unexplained. Sometimes this is also called the noise. So each variable is a function of its parents and a noise, which is not shown in this picture. And the noises are random variables, and these noises are jointly independent, that's the assumption. And everything is deterministic apart from these noises, but from the fact that these noises are random variables, and I should also say this is a directed acyclic graph, we can then, in some canonical ordering, compute the distributions of all these quantities. They all become random variables. We get a joint distribution over all these variables. And it's an interesting joint distribution because it has conditional independent structures that are specified by what's called the causal Markov condition, which I have written here. So the Markov condition in one form, this the so-called local Markov condition, says that each variable is independent. So think of this variable as independent of its non-descendants over here when conditioned on its parents. So all information exchange between a variable and its non-descendants has to go via the parents. So this leads to something which is also called a graphical model, and there are of course great experts on graphical models in this lab here. So this is a graphical model, and one could also say every graphical model with respect to a directed graphical model can be written in this way, but not uniquely. So a functional causal model contains a little bit more specific information than the graphical model. And in a nutshell, without going into detail, the difference is that such a functional causal model also lets us make statements about what's called counterfactuals. But let's not go into this now. Okay, so the central question of causal inference is now the following. Suppose we observe a lot of data, maybe so much data that we can estimate the full distribution. So let's assume we have the distribution describing all these random variables. Can we recover the graph from this distribution? So in other words, can we infer the causal links from purely observational data? That's a tricky question, and a number of people have worked on this, and there's a beautiful theory. People like Pearl, Spertus, Glymer. There's a beautiful theory or a beautiful answer, but not really a complete answer. And there are several. The answer is that if we do, so remember before I told you that the graph structure implies certain conditional independence properties of the distribution. Now we could say, well, how about we just test for these conditional independence properties, and then we can infer the graph structure. There are several problems with it. First of all is that actually the application goes the other way around. The Markov condition says that certain graph properties imply certain conditional independencies, but what we actually want is we want to observe conditional independence properties and infer graph properties from that. People have argued that this is sort of almost an equivalence, or that it would be very coincidental for this not to be equivalent, and people postulate something called faithfulness. Maybe that's reasonable, one can debate about that. It's probably hard to justify for finite data sets, which is an issue that people haven't thought so much about in causality. Next problem is if these functions that sit on the nodes, I told you that in each node we have a function. If these functions are complex, then conditional independence testing based on finite samples actually can become arbitrarily hard. So we shouldn't just assume that we can do it. It's a problem that's as hard as the fundamental problem of generalization in machine learning, where theoreticians have worked for a long time. So in causality, we have been neglecting this, but this is an issue that we shouldn't neglect. And finally, that's the main content of my talk today. If we have only two variables, then there are no conditional independencies. Conditional independence always connects three quantities. So there's nothing we can observe, nothing we can base our inference on. So how can we decide about the causal direction for two variables only? And this is the problem of given two variables, deciding what is cause and what is effect. And of course, a lot of people have thought about this. Starting again from the philosophers, Nietzsche, for instance, said that the error of mistaking cause for consequence is reason's intrinsic form of corruption. So just very briefly, I'll tell you two ideas how to deal with this. First idea is that cause and mechanism should be, in some sense, independent. One can formalize this mathematically, but I'll rather show you a picture to illustrate the idea. So this is this object is called a Boucher chair. It's in the next somewhere, some outdoor art museum. And when we see this object, or when we see any object, our brain makes the assumption that the object and the mechanism by which its light enters our brain are somehow independent. People sometimes call this a generic viewpoint assumption. If we violate this assumption, and here we can violate it by looking through this hole, then we actually see an object that isn't there. We see this chair. So our perception has been misled. There's another nice example here, which is from the National Gallery. It's a painting by Hans Holbein. It's called The Ambassadors. And there's this strange object down here, which, as you look from the very far side, turns out to be a skull. So this was, of course, done to impress his donors or people with this skill of illusionist painting. But I think it's also a nice example of this principle of independence of input and mechanism. So let's assume in the generic case this principle holds true. And then it turns out it tells us something about causal direction. And the idea is, if we assume that our input distribution and the mechanism, so in general we think of this mechanism as a conditional of output given input, but let's do it even simpler and let's assume this is an invertible function, so a deterministic relationship. Let's assume this input distribution and this mechanism are independent. If that's true, then it turns out that the output distribution carries a footprint of the input distribution. In this simple case, for instance, where this carries a footprint of this regularity of this function. Where this function was flat, the output density will be large. This is just an intuitive picture, but one can formalize this various ways. One way is what we've done. We postulate that the logarithm of the derivative of this function here and the value of the density, we assume the existence of a density, both viewed as random variables on the unit interval with respect to Lebesgue measure. We postulate that these two random variables have zero covariance. Then from this postulate we can actually prove that in the backward direction, unless the function is trivial, is an identity, the backward direction we get a strictly positive covariance between the two backward random variables. That's nice. It's an asymmetry, and the asymmetry can be sort of rephrased in various ways that I won't go into detail on. It can be connected to information geometry. Rather, I'll briefly tell you about our second approach, which is based on making an assumption about how the noise influences these functions. So remember, I told you in this structural equation model or functional causal model, each node is a function of its parents and the noise. So let's assume we have the simplest case, just two variables, x and y. Let's assume x causes y. So y is a function of x and an independent noise term. X also has a noise term, but no other parents, so let's actually identify x and the noise term. And just say x and u are independent. If we have such a model, then it still turns out this is an extremely rich model. So for instance, if the noise were discrete, switching between d different values, we could use such a noise to randomly switch between the different mechanisms that transform input into output. So this D could be very large. There's no restriction on the domain of the noise. It could be continuous. It's somehow clear that even with a large set of data, if we don't have restrictions on these functions, and in particular on how the noise acts on these functions, there's no way we can learn this kind of model from data. So one restriction that we have studied is what we call additive noise. So you think of it as a first-order Taylor expansion, where we say this mechanism actually first takes F, processes F with a function, and then adds the noise. And it turns out if we make this assumption, then again we get an asymmetry between cause and effect. So if it's true that if the forward model has additive noise, additive independent noise, and if we additionally hypothetically assume that there's a backward model of the same form that explains the same observed joint distribution of x and y, then it turns out that these quantities involved, the distributions and the nonlinearity of the function, have to be matched to each other in a very specific way, which is highly unlikely to occur in reality. So it's a three-dimensional solution space for which the model can be fitted in both directions. And in the generic case, it turns out that this kind of model is identifiable. So I'm going to skip this one. Well, so before I was telling you that we can do conditional independence testing to learn something about the graph structure. So typically the answer is, if we do the conditional independence tests, if we assume faithfulness, we can infer a equivalence class of graphs that are consistent with the conditional independencies that were observed. It's normally not a single graph, but at least a set of graphs. And in some sense, the idea, one intuitive way to think about it, is that we have injected independent noise everywhere. Remember, each node had a noise variable. The noises are jointly independent, and then we let them spread through the graph and then measure in different places what arrives where and how do these different informations relate to each other. So that's one way to think about conditional independencies. The new things that I told you about, new ideas or potentially new ideas, is that rather than just checking independence of noises, we can also think about independence of noises in functions. So I told you about this idea of independence of the mechanism and the input. So these noises, as they spread through the graph, they pick up information not just about the graph topology, but also about the functions by which the noises were transformed as they passed through the nodes. And I think that's something interesting to think about more. I also talked about restricting the function classes. We have also thought about how to combine these aspects. I think I'm not going to talk about this in detail. We have thought about an approach that uses algorithmic complexity or Kolmogorov complexity instead of Shannon information or probability theory, which leads to something like graphical models in terms of Kolmogorov complexity, where on the nodes we don't have functions. We don't have functions processing probability distributions, but instead we have programs processing bit strings. And independence of bit strings is measured by whether we can gain by jointly compressing bit strings, etc. And one can develop something like graphical models or causal graphical models in this setting as well. But rather than talking about this, I want to briefly tell you about how causal knowledge can help machine learning, because my long-term goal is really to combine causality and machine learning. And I'll have two examples. One, very briefly, about semi-supervised learning and distribution shift, and the other one is in the field of exoplanet detection. So it turns out that in some machine learning problems we are learning to predict effect from cause, and in others it's the other way around. We predict cause from effect. Actually, it seems to be more often the latter. And we could call these problems causal and anti-causal. So for instance, digit recognition is an anti-causal problem because we decide in our head the class label, and then we produce the digit. So the digit is the effect, the class label is the cause. So the direction of prediction is the opposite of the direction of causality. In some other problems, they are identical. Now it turns out if you think about these two settings that that actually makes a difference for practical machine learning problems. So in general, whenever we want to estimate a mapping from x to y, we have to estimate properties of the conditional of y given x. Now remember the causal assumption that I made before, that the distribution of the cause and the mechanism should be independent in some sense, where one can formalize in various ways. Now in semi-supervised learning, I think you might know this, but for those who haven't heard about it, the idea is we want to improve our estimate of this quantity by having more data from P of x. Covariance shift, on the other hand, assumes that P of x changes between training and test, and P of y given x might or might not be robust. Now let's think about these two settings. If we have a causal learning problem, then we assume that P of x and P of y given x are independent. So in the causal case, x is the so prediction and causality are aligned. So x is the cause, y is the effect. So we assume this independence, which means that semi-supervised learning should be impossible, because in semi-supervised learning we have additional information from this in order to improve our estimate of this, but if they're independent, that's pointless. On the other hand, covariance shift should be easy, because our causal assumption actually precisely says that P of y given x is not affected by P of x. So if P of x changes, P of y given x should be invariant under this change. That's nice. It turns out in anti-causal learning it's exactly the other way around. In anti-causal learning we have this kind of independence, which implies, as I mentioned before, a dependence in the backward direction. So semi-supervised learning might be possible, but on the other hand, covariance shift should be harder. And I don't show data, but we've done a meta-analysis looking at benchmarks of other people and categorized their data sets into causal and anti-causal. So usually people in machine learning are not interested in that. If we do that and look at the benchmark results, then this is very much consistent with this prediction, which is nice. And also the various assumptions that people have come up with to justify semi-supervised learning can all be interpreted causally. So that's also nice. Okay, finally, last application, which is from exoplanet detection in astronomy. So that's a problem we've been very much interested in lately. And the problem is the following. So there's this space telescope, which was launched in 2009. So this is where we are in the Milky Way. The Space Telescope was launched in order to observe a tiny fraction of our Milky Way, staring in this direction all the time in search of exoplanets. So if you look at the search field, this is somewhere close. This is the Milky Way. This is the constellation Cygnus. And the telescope was looking at this patch here with a set of CCDs, which are close to each other. So charge coupled device imaging sensors for about 4 years. So in this field, it's taking pictures, or it was taking pictures, a series of 30-minute exposures essentially. Each picture looks like this. You can see the stars. On each picture, I think there's about 500,000 stars, and out of these, the astronomers declared 150,000 for interesting and extract time series, because we have this series of exposures. So for each of these 150,000 stars, we get a time series. This telescope is called Kepler, after the astronomer Kepler. And now we have this big data set, and what we're looking for is transits. So what's a transit? Imagine there's a star somewhere out there. The star has a planet, and we happen to look at the system from the side. So every so often the planet passes in front of the star. If you think about what kind of signal this would produce, if you looked at our system of Earth and Sun from space, you can work out that it would be an 84 parts per million signal, just from the size of the Earth. The diameter of the Earth is about 1/100th of the Sun, so it's 10 to the minus 4 roughly. It would last about half a day, the signal, and you have to be lucky to see it, because it would be visible only geometrically from 0.5% of all directions in the Milky Way. So this is the kind of signal we're looking for. It's a relatively faint signal, which is why you have to do it why it's better to do it from space, because if you look from the ground, you have all these atmospheric disturbances. But even if you do it from space, it turns out the errors caused by the spacecraft and by the stars are actually more variable than we used to think they are. So these errors actually lead to changes that are sometimes much bigger than the signal we're looking for. Nevertheless, this space telescope has found many planets. Some of them are considered habitable in the sense that they allow liquid water. They are at the right distance from their planets, but those are all around stars much cooler or smaller than the Sun, because that means the habitable zone is closer, a year is much shorter, and then we see more of these events, which gives us a better statistical power. So each star projects light on a number of pixels, and if we look at these pixels, so this is, for instance, all belonging to the same star, and these are all little light curves of these pixels. Unfortunately, all these curves look quite different, and this looks quite hopeless. It's due to various errors, and the biggest one is probably telescope pointing. So the pointing is exquisitely accurate, but nevertheless, small changes of a fraction of pixel, together with the fact that the pixels' sensitivities are different, lead to these, this is scaled up, of course, but they lead to these different behaviors of the pixels. And the astronomers have developed a data processing pipeline to deal with this kind of systematic errors. They have something they call PDC, pre-search data conditioning, and then they put together these things, process them, and they get light curves like this. And you can see an exoplanet, a little transit here. This dip, actually it's not a little one, this is a big one, because this star actually has 3 exoplanets, and the other 2 I think we don't even see here, because it has one that has a period of 8 days, and this is about 30 days, so we should see some small ones that we don't see here. Anyway, so this is the kind of data that we're looking at, and it's a difficult problem, and we thought about this from the causal point of view, and I want to motivate the method with this little illustration done by my wife, and so the idea is we try to reduce these systematic errors, and we do it in the same way as this problem here. Suppose you see this picture of 5 siblings. So there are some statistics, this probably doesn't apply to England, but the statistics say that up to 20% of all children have an unexpected father. Now, in this case, it might be easy to tell which one. But there's a slightly harder problem. And this harder problem is, how does the milkman of this family look like? And in our astronomy application, what we want to do is essentially we want to reconstruct the milkman from the picture of many siblings without knowing the mother. So here I have a little graph, what we want to do. So this is the observed star. This is what we want to infer about the star. This is the noise. So unfortunately, the mother plays the role of the noise here. But we see many potentially other siblings here. And now the idea is that we have to assume actually that the milkman and the other siblings are not related. The idea is that we try to predict properties of the one child or of the observed star from the other stars. And then whatever can be explained must be due to the fact that they're both caused by the same noise process. Since the true star is causally independent of the other stars and therefore also of the measurement of the other stars, whatever we can explain by explaining this in terms of that has nothing to do with the true star. So the idea is now we perform regression of y on x, and then we remove somehow this regression from y in order to reconstruct q. And that sounds optimistic, but it turns out under suitable assumptions we can prove that this works, which surprised me, but in retrospect maybe it's not so surprising. And the assumption is again an additive noise type assumption. Assumption I've told you already about, this independence of the milkman and the children, the other children. And finally we have to make the assumption that the effect of the noise can in principle be predicted from the other stars. So there exists some function psi such the effect of the noise is that function of the other stars. We don't need to know that function. So in principle, it should be the case that the effect of the mother is visible in the other children. Under these assumptions, we can prove that we can reconstruct Q up to a constant offset by simply subtracting the regression from y. And it's nice, we can reconstruct the full random variable with probability 1, not just the distribution, but the actual, all the values, by doing this simple regression. And we can slightly generalize this by relaxing this assumption here that the effect of the noise is fully predictable, if we relax it, then we can still prove that, roughly speaking, if we can, in principle, so if X determines the effect of the noise with small variance, then we can prove that we get a good reconstruction in terms of small mean squared error. But maybe let's not go into details on this. Instead, just one picture here. So here, this was what the astronomers so far did. This is now our curve after taking out these systematic errors. We think it looks nicer. The astronomers like it. We are still working on this problem. It's a complicated problem. You need to not just normalize the curves, but you also need to have a model of these dips, and you have to do this periodic search, etc. And we have a more comprehensive system that is doing all this, where we have recently produced a list of candidate planets, and some of them have already been confirmed. So that's nice. So I promised, coming to the end, promised I will come back to this citation. So this quote, which was maybe a somewhat naughty description of machine learning, of what machine learning is doing, is actually from this philosophy website, and is a description of what people call a cargo cult. So a cargo cult is a term for what happened in some Pacific islands. I think it was, for instance, described by Feynman, where people started to associate certain objects and acts with cargo arriving. So the airport landing strips, people waving flags and things like that, were associated with positive things that came from the skies with American soldiers. And afterwards, when the soldiers didn't come anymore, the islanders were still waving flags and doing things like that. So, which is sort of, they observed this correlation. They tried the intervention of waving flag, didn't work. So it illustrates the difference between machine learning and a causal model. Now, of course, if you apply machine learning in the right way, it would still be valid. So if you had a generative model that produces lots of Pacific islands and tells you on which islands are there people waving flags and landing strips, etc., then probably you would be able to predict, at least if you sample from the right time when this still happened. So distribution shift is not allowed. We have to do IID. Then you would have been able to predict whether there is cargo or not. So if you apply machine learning the right way, and we have become very good at generating IID data. Like big companies are paying people to label data. I bet Microsoft is also doing this in order to train machine learning systems. So if we do it the right way, then of course it's extremely powerful. But at the same time, I think it's interesting to think about what we can do if these assumptions are violated. And I think that causality is one interesting direction to consider in this context. And with that, I would like to acknowledge my co-workers and thank you for your attention.
Well, we have a little time for questions from the audience, if people have questions for you, Bernhard. It was a fascinating talk. Yes, Elon.
So we now have ability to run mass experiments with all sorts of web scale and stuff like that. And that has particular power to learn causality. How would you compare that power to the power of methods you were describing? So if of course, you can handle cases where you cannot do experiments. But if you could do experiments, would there be one that is very dominating?
So I think if you can do good experiments, then that will certainly be preferable to these kind of methods, because all these methods that I talked about, they need assumptions. In the simple case, cause-effect inference, we think that it works maybe 80% correct. But if you can do a controlled, randomized experiment, then I think you are much, much closer to the ground truth. So in these situations, I think it's great to do these experiments, and I agree. Nowadays we have the means to do this in many domains. But as you also say, there are many domains in neuroscience, etc., where we can't do this kind of experiments. So I think from practical point of view, if you can do them, it's better. From purely scientific point of view, if you're interested in inference, it's very interesting to think about fundamentally how far can we get without these experiments. I think it's a hard problem. It's also a hard problem for humans to perform causal inference if we cannot intervene in the system. Yeah.
Yes.
So, in your motivating example, you mentioned the storks and the babies. Well, the idea was that there must be some sort of other factor that we're not observing that influences both the storks and the babies. So if you perform inference on those graphs in terms of, and your goal is to find causality between the nodes that you observe, obviously you will not find, in some cases there will be, in some problems there will be other factors that you're not observing. Is it possible that are there methods out there to at least detect the existence of such factors and determine, say, how many of them there might be, or which nodes they might be connecting, and so on?
Yeah, I think the answer is there are some, but it's very much an open problem from my point of view. So I think it's one of the most interesting problems of causality, and I haven't talked about it today. How to detect whether there are confounders, maybe how to bound the effect of confounders if you're willing to make certain assumptions about how the confounding works. I could send you some things if you're interested. I think it's very interesting problem for sure. Yes.
Any other questions? Yes.
I have a question that's a bit of a follow-up to Elon's. So you said that doing the intervention is always preferable, but at the same time that may be very expensive. So if I only have a limited capacity for running experiments, could I maybe use your methods to figure out what I should test next? Or is there any work in this hybrid space that kind of bridges between the two?
Mm-hmm. Yeah, I think that would be interesting. Yeah, I think that some people have thought about this kind of problem. So I haven't studied that myself, but I think that's also an interesting direction. Yeah. So how can you? I don't know whether people understood in the back. How could you combine the possibility of doing some experiments that might be expensive with this kind of methods that might suggest directions to explore or suggest what might be causal directions, etc. Yeah, I think that would be certainly useful to combine. Yeah.
Any other questions? I heard Bernhard lecturing recently at the Royal Society, where he won the Milner Award, which is the top European award in computer science, only been given 3 times, and the lecture was followed by refreshments, and so I infer from that a lecture by Bernhard causes refreshments to be served, and indeed that is the case today, so let's thank him and then go and enjoy them.